Well, hello everyone. Sorry if you hear my voice not that well. I think altitude sickness has affected me a bit, but we'll try to do the best we all we can. Right, so I am a PhD candidate in financial computing at University College London, and I'm also a research fellow at the DLT Science Foundation, which now is known as Exponential Science. Before I go directly into the research, I want to provide some background information about AMMs. So for example, if we look at the taxonomy of the whole D5 ecosystem, and if we map some of the existing platforms, you would see, for example, some of the lending platforms and some of the main automated market makers. At least for this research, the main focus, the main emphasis will be around the ones that use the constant function, where you would see Uniswap v3 there, or Uniswap v2, whichever version, and of course Bancor, which is the one who started all of this about constant function market makers. Now, if we relate this to a limited order book, first to give you as a context, so for example, this is the limited order book of Binance. You see the buy and sell orders, and then of course you see at the middle here where the mid price is, that there should be a market maker here doing the bid-ask spread between the buying and selling orders, and they of course make some profits from doing that, but at the same time that keep the price synchronized within the market. Take that in mind, because that will be relevant for the next piece once we compare it to when we look at automated market makers. So the automated market makers came with the idea that we can remove the market maker, and we can have this structure when you can provide the liquidity either from, you can say from price zero all the way to infinite. This is the one initially introduced by Bancor in, I forgot the year exactly, but it was Bancor, and was made popular by Uniswap v2. And then Uniswap v3 incorporated this idea of concentrated liquidity, where you can put, as a liquidity provider, put liquidity between specific price ranges. So if we want to, for example, take these AMM-based DEXs, we can tweak things around, and then we can have this visualization in a way of a limited order book. Now, getting more into some of the math-related things, so even though, for example, you might have different implementation on automated market makers, such as the geometric mean market maker and the constant product market maker, if you simplify both formulas, at the end of the day, both are just a multiplication of two tokens and remain it to a constant. Where, if you plotted this, it will be this bonding curve, where the price for it is defined by the slope of the constant function. Of course, that price changes depending on the interaction with the market. And then if we go in more detail, and then we look at Uniswap v3, it looks a bit more complex, because they incorporate this idea of having a virtual curve and also having a real curve. Here is the actual tokens that you deposit, and then this virtual is with the purpose that you can have, for example, the liquidity more concentrated. So if we look this will be, for example, the active, so where all the trading is happening in the moment. But for this, for simplicity, you can say that at the end of the day, Uniswap v3 and v2 function, they look the same when you look at the active tick. So just to give you as a general background of some of the terms that we're going to be using. The spot price here is just the slope of the bonding curve function, and then the price impact is the price that you end up executing your trade versus the price that got quoted to you. And this is relevant in terms of a slippage, which is one of the main issues that you have in this constant product functions, which was highlighted before by some of the people that presented. And let me show you. So why that is, why you have issues with price slippage, and how that affects you as a trader or as a liquidity provider. So for example, if we plotted the price that you have in Binance, which uses a limited order book, and the price that you can go and look at Uniswap that gets quoted to you, you might notice there is a difference between the prices on both of them. And that difference is mainly defined by the next block confirming the transaction. So that creates a time lag difference that can be taken advantage by arbiters. And that time lag difference at the same time, it leads to slippage. And there is a relationship between the slippage and as well impermanent loss for liquidity providers, which I will not go into more detail, but I recommend you this paper. It's a more finance quant related, but it goes in more details about that. Now, for this research, our main desire was to see, well, we have two automated market makers, one below the protocol level of the XRP layer, which is 4 seconds in processing time, and then we have Uniswap v3 running on a smart contract on Ethereum, which is around 12 seconds. So does it make any difference for liquidity providers and for traders? So, because some of the solution, at least in the literature, proposed to solve for the issues of arbitrage is either you have a blockchain with faster block times, or you can have dynamic fees so they can adjust to respond to the market, or you can, for example, include auction mechanisms that can redistribute some of the fees to the liquidity providers, and that can reduce the impermanent loss. So at least for this example, given that the XRP layer went and implemented their own AMM, we were curious to see if this does it make any difference if the blockchain is faster, does it make any difference if it is implemented at the protocol level, and does it make any difference as well if you have an auction mechanism. Just to give you just as a general reference, so when I say at the protocol level, when you think about the existing AMM-based DEXs, most of them are implemented here at the application layer based on smart contracts. But for this, that we are testing is implemented here at the infrastructure layer, so which could mean that you have you can take advantage of native transaction fees and speed, because you don't have to deal with some issues like network congestion that would normally be if you are competing, if you have a smart contract with a heavy payload, for example. And also at the same time, there are some other vector attacks that's very relevant and depending with the blockchain that you're working with. Specifically, these ones, like a front-running, back-running sandwich attack, and block transaction manipulation and sequence, that's very specific to Ethereum because the mempool is transparent and there's an incentive for the miners to decide the order of the transactions. So for the continuous auction mechanism, just to give you a quick example, this one refers to a trader receive a 24-hour slot that they can decide to use to increase their trading. So with the idea that the price synchronization with the external market can be tighter than having to wait for them to have all the incentives. So we do some simulations where we generate different price data, different volatilities and scenarios to compare and to see if it doesn't make any difference and how does that look like. And our results, what they show is that as intuitively you would expect, the block confirmation type or interarrival time, or however you want to define it, it does make a big difference to have a price synchronization better with an external market, and at the same time reduces slippage, and then that you can translate into improvement in reducing impermanent loss. And we do some empirical validation as well, taking some Binance data at the second by second level, and we find the same results as well. And then also that's congruent with existing literature. For example, this is another empirical paper that shows that you need shorter block times in order that you can reduce arbitrage losses. And so for example, you can see here, once you increase the block interval in seconds, your losses start increasing. So it's very relevant to have and at the same time you can compare it with, it doesn't matter which liquidity pool you look at the end of the day, it's important that the underlying blockchain where your AMM-based DEX is running to be faster. And this leads me to the next thing. So we started our research around 2023, early 2023, and then we saw late last year that Unichain from Uniswap got launched. And then if you read the white paper, they emphasize a lot this part, they want to achieve 200 to 250 milliseconds effective block time. So that's relevant given the context that I was giving to you. And then also, they want to increase the mempool to avoid the extra incentives that miners have for some of the front-running, back-running, and sandwich attacks that at the end of the day, it just create issues for the liquidity providers. So as a final conclusion, I would say it's very important for an AMM-based DEX, the infrastructure blockchain that it's using. If it is faster, it's better. But at the same time, I understand and raises other questions that if you want to make a blockchain faster, you might have to sacrifice something else, and that could be decentralization. So, question open there, at least for us, or for the purposes of this research, we find that you need a better, faster blockchain, independently of how you're running your AMM-based DEX, whether that's with the smart contracts or with that's at the protocol level. So this is the link for the full paper. If you're curious to read it, it provides more details. I will say this version, I have not updated to the latest version, but it will give you the general details. And also my contact information if you have further questions.
Lovely. Thank you very much, Walter, for taking time to take us through DEX architecture. Very deep and insightful. And I hope you can make a quick recovery with your voice.